Welcome to ePathshala lecture series on computer science. In this module on data analytics, we will continue discussing about the fundamentals about data analysis. As part of this discussion, we will understand what exactly is bivariate analysis and multivariate analysis, the need behind these analysis. The objectives of this module are: first, the audience will be in a position to understand the basics of bivariate analysis, followed by the need for a multivariate analysis and the fundamentals behind the multivariate analysis. After doing these two analyses, we will also understand what is the need behind normalizing data. So, we will be discussing about various methodologies related to data normalization. Now, let us start with bivariate analysis. As we discussed in the previous module, univariate analysis is associated to analyzing a data with respect to a single attribute, but bivariate analysis is analyzing the data with respect to two attributes. So, we are going to consider two attributes at the same point of time. Normally, when we take a data and when we are trying to analyze the data with respect to two attributes, what is that we are trying to identify from these two attributes is we are trying to extract or identify associations or dependencies between them. And in case if there some exist, then such dependencies will be extracted out. Now, given a data with two attributes, how it can be represented mathematically? So, a data with two attributes and its corresponding value may be represented as shown in this matrix. So, the data D may be represented using an n by 2 matrix, where 2 indicates the number of attributes or parameters with which we are trying to analyze the data. Geometrically speaking, we can think this data matrix D in two ways. It can be viewed either as n points or vectors in a two-dimensional space, which is associated to the two attributes x1 and x2. Now, with respect to the data that we are trying to analyze having two attributes in our mind, what are the metrics that may be used for analyzing this data? As discussed in univariate analysis, the same metrics and measures like location and dispersion measures, for example mean, variance, covariance, etc. may be used. Now, let us understand what is mean with respect to a bivariate data. The bivariate mean actually is defined as the expected value of the vector which is associated to the random variable x. Since we are having two attributes which are considered to be two random variables, we can have two means associated to the given data. So, mathematically the mean is represented using the notation mu, which is the expected value of the vector random variable x. Since x has two attributes, therefore, we will be having two expected variables, one for x1, another one for x2, and therefore, we will be ending up with two means for the two different attributes. Having identified what is the mean, then we can easily derive what is the variance. Variance, as we know, it is the difference of the data with respect to the mean. Since in bivariate environment we have two attributes, we have got two means. Therefore, we need to analyze the attributes with respect to their respective means. So, the difference of one attribute with respect to its mean and the difference of the other attribute with respect to its mean will provide the variance for a bivariate environment. So, naturally we end up with two variance. One is sigma 1 square for the first attribute and sigma 2 square for the second attribute x2. So, these two attributes may be mathematically represented for their variance. Given these two attributes with two different variance, then we can always derive the total variance. The total variance is given by the sum of the two variances for the two attributes respectively. The next measure is measure of association. We discussed about variance, and we all know variance is actually a measure with which we identify the deviation of a data point with respect to its mean with respect to a specific dimension. For example, we can consider height as an attribute. We may have set of heights related to set of individuals. We can identify what is the deviation of these heights or individual height with respect to the sample's average height. This will provide a variance. With the variance, we can go for covariance. Covariance normally comes whenever we are having two attributes for the purpose of analysis. So, we are trying to identify how each and every dimension and the values in those dimensions vary with respect to the dimensions mean. So, this is what is called as covariance. So, covariance is measured between two dimensions to see if there is any relationship among the two dimensions. These relationships may be in turn used for further analysis or for decision making process. For example, we can take two attributes, one the number of hours studied and the other one say the grades obtained by a student. So, we can collect a sample from say a population set, assume the sample contains students and the students are associated to two attributes, one is the number of hours they have spent for the exam and the grades that they have scored as part of the exam. Now, we can try to identify is there any association between these two attributes, that is the number of hours studied and the grades obtained. So, how we can mathematically represent a covariance? Covariance, when we are trying to represent with respect to a single dimensional environment, then it itself is its variance. So, we can take a variance equation which we discussed in the previous module. In the variance equation, we find say when a particular attribute's mean and the difference with respect to its mean is computed, it provides a variance. But with respect to covariance, since we are involving two attributes, one will be the attribute 1 and the second parameter will be decided based on the attribute 2, that is the first random variable x and the second random variable y. So, therefore, covariance between the two attributes x and y is as shown in this equation. So, it is nothing but the difference of the attribute's value with respect to its mean and the difference of another attribute's data point with respect to its mean, that whole divided by n minus 1. Once we have derived the covariance, how these covariance values may be represented? So, covariance can be represented using a covariance matrix. This covariance matrix for a two dimensional environment is going to be a 2 by 2 covariance matrix. So, we have sigma 1 square, sigma 2 square and the covariance between sigma 1 and sigma 2. In other words, it is the covariance between dimension 1 and dimension 2. Similarly, the reverse way between the difference between the dimension 2 and dimension 1. So, when we take a look at this covariance matrix, we find the matrix is going to be a square matrix, and since in this matrix this sigma 1 2 and sigma 2 1 being the same, therefore, this matrix is considered to be a symmetric matrix. Now, when we are trying to work with respect to this covariance matrix, what are the information that we can infer from this covariance matrix? The covariance matrix actually records two different types of information, one along the main diagonal. So, that is the sigma 1 square and sigma 2 square. This main diagonal actually identifies the attribute specific variances. So, sigma 1 is the first attribute, sigma 2 is considered to be the second attribute, the standard deviation related to second attribute. Now, these two indicate the attribute specific variances and this is recorded along the main diagonal. And we have an off diagonal element which is represented using the sigma 1 2 and sigma 2 1 value. This off diagonal values actually provide information about the covariance with respect to the two dimensions. So, from this matrix you can find sigma 1 2 and sigma 2 1 are associated to the two different dimensions 1 and 2 respectively. Having identified the covariance with respect to individual dimensions, now we can calculate the total variance, which is going to be the sum of individual variances. The next type of measure which may be used for quantifying association among dimensions are correlation. Correlation between two variables, say x1 and x2, is considered to be a standardized covariance which is obtained by normalizing the covariance with respect to the standard deviation of these two attributes or variables. So, mathematically we can consider this correlation by this equation. So, here it is nothing but in the numerator we have sigma 1 2 which is say the covariance related to both the dimensions, and in the denominator we find the covariance with respect to a specific dimension sigma 1 and the covariance with respect to the second specific dimension sigma 2. The cosine of this correlation is going to provide an angle between these two covariances, that is the angle between these two dimensions. Now let us take a sample data. Consider the iris data set. Iris data set actually provides detail about sepal length, sepal width, etc., and this is all related to, say, data set that is already available over the web. So let us take this iris data set. A sample of the iris data set is shown in this chart. The values 5.9, 6.9, 6.6, 4.6 and so on are nothing but, say, the sample length which is available as part of the iris data set. So here from this data set we actually consider only one variable, which is sample length. The total number of attributes and the corresponding values collected here are 150. So we are considering the sepal length, and for the sepal length we have considered 150 samples. Now we can easily compute what is the sample mean. So now for this single data, which involves exactly one attribute, the sample mean will be the sum of all these values for this attribute divided by the total number of sample. So it is these individual values 5.9 plus 6.9 plus 6.6 plus 4.6 till 5.1, the whole divided by total number of sample is 150, which is approximately 5.843. The next measure is median. Median, as we all know, it is, say, the middle element in a sorted fashion. So for a given sorted data, what may be the middle element? This data that you find in this chart is actually not sorted. Once you sort and then identify the middle element, then we may end up with the mean. So for this 150 number of data, we first need to sort them. Since it is 150 in number, to identify the middle element, we can divide 150 by 2. So it is going to be 75. And since this is even numbers, that is total number of elements in this sample is even, we need to take n by 2 as well as n by 2 plus 1 position. So therefore 75 and 76 are the two positions, and we need to consider the values available in the 75 and 76th position in this sorted order. Both the values, that is in 75 location as well as in 76th position, we find 5.8 as the value. So the median for the sample data set is going to be 5.8. Next metric is mode. Mode is nothing but the most frequently occurring data or value as part of the data set. When we analyze this data set and when we represent the same in the form of an histogram, we may find the value 5 has occurred many number of times. So from this histogram we find value 5 occurring more number of times. So therefore we can fix the mode for the given data set to be 5. The range for the given data set is going to be the minimum and maximum values. The minimum value as indicated in this chart is going to be 4.3, and the maximum value indicated in the chart is going to be 7.9. Therefore the range is going to be 7.9 minus 4.3, that is the difference between the maximum value and the minimum value, which is 3.6. Accordingly, now we can calculate the variance and standard deviation. So the variance, as I already mentioned, it is the difference of the data point with respect to its mean. So we calculate the difference, square the difference and sum all these squared differences, which will be divided by the total number of elements. So it is equal to 0.681, and the standard deviation is going to be the square root of the variance, which is 0.825. So for the given data set, which is going to be univariate in nature, we have once again analyzed what are the various metrics and what values these metrics may take. Now let us increase the dimensions. For the same iris data set, now we are going to take two dimensions. One is the sepal length, which you have already seen, another one is the sepal width. Now when the sepal length and sepal width are plotted, it may look like this graph. Now from this graph, what is that we can derive is, we can derive various measures like mean, covariance, covariance matrix, and then the correlation. Since there are two dimensions or two variables, therefore we end up with two means, mu1 and mu2, one for sepal length, another one for sepal width respectively. Mu1 will be 5.84 and mu2, that is average for the sepal width, will be equal to 3.054. With this mean, now we can compute the difference or deviation of each and every data point along the respective dimension with their differences. These differences when summed together, we can end up with say the variance. With the help of variance, now we can calculate the covariance matrix. So, the covariance matrix will be a 2 by 2 matrix since it is associated to two different variables, sepal length and sepal width respectively. Now, when you take a look at this covariance matrix data, we find the sepal length covariance is going to be 0.681, which is represented by sigma 1 square, and the sepal width covariance is going to be 0.187, which is represented as sigma 2 square. With this covariance matrix, now we can define what is the covariance between the two attributes, that is the sepal length and sepal width, which is recorded along the off diagonal element. As discussed previously, the main diagonal element will highlight the covariance with respect to a dimension, and the off diagonal elements record the variance with respect to two attributes. So, the covariance with respect to the two attributes sepal length and sepal width is going to be minus 0.039, and from this itself we can find it is going to be negative in nature. Having identified the covariance between the two attributes, now we can derive the correlation between the two attributes, which is say the normalized value with respect to the covariance of the two attributes divided by the square root of variance of the respective dimensions or attributes. So, which is equal to minus 0.109. Now, when we have identified the correlation, we can always identify what is the difference in terms of angle, which is defined by the cos theta value. So, cos theta of this minus 0.109 is going to be 96.26, which is approximately 90 degree, which indicates they are orthogonal to each other. In other words, they are not having any good correlation. In other words, they are indicating weak correlation. And also the negative value indicates say it is very weak in nature, and hence these two dimensions cannot be used for the purpose of any further analysis. Having understood what is a bivariate analysis, now let us start with multivariate analysis. Why there is a necessity for multivariate analysis? Majority of the statistical techniques consider one or two attributes for their analysis, but this may provide an erroneous output. In order to overcome this, we go in for multivariate analysis. In multivariate analysis, we discussed or we consider more than two variables for the purpose of analysis. Now, this may be understood with the help of Simpson's paradox. Consider a university which is admitting male and female candidates into their courses, into the courses which is run by that university. Now, a sample statistics about the male and female candidate who have applied, who have got accepted, that is they have been admitted, and the percentage of male and female candidates who were rejected for admission into certain courses is summarized in this table. From this table, we find say 44% of male applicants are admitted into the university, but only 33 female applicants are admitted. So, from this data, there is a chance that we may end up with a wrong conclusion that the university is following say an unfair admission system. What does it mean? Is there any discrimination with respect to the sex? So, what is that we need to do is, we need to take this data. Currently, we are analyzing the data with respect to two attributes. One is sex of the candidate, another one is based on the admission. With respect to these two attributes, we may end up with this wrong conclusion, that is there is some sort of discrimination with respect to male and female candidate who apply for a course, admission into a course. Suppose if we do the same analysis by considering or by drilling down into this table with additional attributes, then we will find is there a chance for disproving this claim. The university can now analyze the admission data with respect to say the department into which admission is sought. So, here there are two tables available in this slide. One table is with respect to admissions into engineering courses, and another table is all about admissions into say non-engineering department, say for example English. Now, when you take a look at the data, you may find a completely different scenario, but even from this we can come to a conclusion there is no relationship between sex and the acceptance in any of the program, either into the engineering or into the English. Now, how this may be proved? The reason is, when you take a look at say the engineering, we find less number of female candidate applying for engineering and more number of female candidate applying for non-engineering department, which is not easily concluded or which may not be derived from the previous table. So, now what is that we have done is, we have considered one more attribute or one more dimension called the course into which candidate is applying for admission. With this, we can say when more than two attributes are brought into picture for the purpose of an analysis, we may end up with say a correct conclusion. So, what exactly this Simpson's paradox indicate? When we are analyzing a data with respect to the whole data, we may come up with one conclusion, but if the same data is analyzed with say the partitioned sample, then we may end up with contradictory conclusion. So, this is useful for explaining how multivariate analysis may be useful for our analysis. So, this analysis can be pictorially represented like this. Say there may be two attributes, one may cause a change in the other attribute. So, here A and changes in A are actually associated to B. So, changes in A cause changes in B. There is another scenario, there may be a common response, that is changes in both A and B are caused by changes in the third variable. But this may be confounding because changes in B are caused both by changes in A as well as by changes in the third variable C. So, we can model the entire scenario with respect to say a third variable C and how it affects the other two variable. So, from this what we can conclude is, when we are trying to do bivariate analysis or any analysis that involves single attribute, we may have misleading results. So, in order to overcome this, we need to add few more variables or attributes for the purpose of better understanding of the data. So, this results in the multivariate analysis. Commonly when we take any survey, we find often these surveys are associated with approximately at least 200 variables or 200 attributes. Now, when we are trying to collect data, say a researcher is associated to data collection, the researcher may not know what data may be useful, what data may not be useful. Therefore, the researcher will start collecting data and that may result in say some n number of or high dimensional data. In such a scenario, when we are trying to take few of the attributes, say for example one or two attribute for our analysis, then we may end up with wrong conclusion. So, multivariate analysis at this scenario will come to a help. So, multivariate analysis, shortly called as MVA, can help summarize the data and it also helps in reducing the chance of obtaining spurious results. There are two types of multivariate analysis techniques. One is analysis of dependence, another one is analysis of interdependence. What is exactly analysis of dependence is, when one or more variable are dependent variables, then their dependency can be explained or predicted by the other variable. For example, we have multiple and partial least square regression techniques and also multiple discriminant analysis, which are closely related to analysis of dependence. Analysis of interdependence is, no variables are thought of dependent. So, what we can do is, we can consider the data points as independent of each other and accordingly we can identify some sort of interrelation among them. So, best examples for analysis of interdependence are cluster analysis and factor analysis respectively. Having understood the necessity behind multivariate analysis, now let us discuss about the fundamentals of multivariate analysis. So, in a multivariate analysis, the data that we are considering of course will have n number of attributes or dimensions. Now, when we represent the same using a data matrix, the data matrix will look like this. Here we can take the data matrix and we can see the row as a set of n points or vectors in the d dimensional space. But when we analyze the same data column wise, then we can consider the same data as a set of points or vectors in n dimensional space, which is spanned by the data points. For the multivariate data, similar to univariate as well as bivariate analysis, we can derive various metrics like mean, covariance and total variance. So, the mean for multivariate data will end up with say n number of mean according to the number of attributes. Suppose if you are going to have d attributes, then we will be ending up with d means. The covariance matrix is going to be a square matrix and squared symmetric matrix of having dimension d by d, since we are having d attributes for the data. The total variance hence may be defined as the sum of the variances with respect to the respective attributes. Here in this covariance matrix, you can find the diagonal elements actually specifying the covariance with respect to a specific dimension or attribute, and the off diagonal elements normally represent the covariance between attribute pairs, say for example xi and xj. Let us take the example of the same iris data set. The source for iris data set is provided here. From this data set, we have considered all possible attributes which is part of the data set: sepal length, sepal width, petal length and petal width. Originally for univariate analysis, we associated ourselves with sepal length attribute. Then for bivariate analysis, we associated two attributes, sepal length and sepal width. For multivariate analysis, we are going to consider all these three attributes and the corresponding value. So for this multivariate data, what may be a multivariate sample mean? Since we are having 4 attributes, therefore we end up with 4 different means, and accordingly the covariance matrix will be a 4 by 4 matrix. The diagonal elements of this covariance matrix highlight the covariance of a specific attribute, and the off diagonal elements represent the covariance across attributes. Here in this scenario, it is between pairs of attributes. So 0.681 is the covariance related to say the sepal length. 0.187 is the covariance associated to sepal width attribute. 3.092 is the covariance associated to petal length, and 0.579 is the covariance related to petal width attribute. The rest of the off diagonal elements, for example minus 0.039 is the covariance between sepal length and sepal width. Similarly, this second element minus 0.039 is also the same. This is the covariance between sepal width and sepal length in the reverse order. Once we have computed the covariances for various dimensions, now we can calculate the total variance for the entire data. So the total variance here is going to be the sum of all these covariances, which is equal to 4.539. Having understood the necessity for univariate, bivariate and multivariate analysis, we can identify the associations among various attributes in the given data set. But actually speaking, when you take a data and when we go through the values, we may find the attributes value may be having different scales. Therefore, we need to identify a methodology by which we can normalize the data. So this results in data normalization, which is very essential when we are dealing with multivariate attribute. So in data normalization, what we do is we take 2 or more attributes that are often different in terms of their scale. Then we try to normalize these values. So what we try to do is we apply few techniques like range normalization or standard score normalization for the purpose of normalizing the data to a specified range. Normally, we normalize the data in the range of 0 to 1. Let us discuss how range normalization works. Suppose you have a variable x and the values for this variable x1 till xn. How we can scale down is we can always apply the equation x is equal to xi minus minimum of xi divided by max xi minus min xi. Here this min and max are nothing but the minimum and maximum values of the corresponding attribute x. So this x dash I is the new value for the given value xi. So after performing the transformation, we now find the values in the range 0 to 1. Similarly, in standard score normalization, what we do is this standard score normalization is also called as Z normalization. In Z normalization, we normally make use of the sample mean and the sample variance. So sample mean mu and sigma square, the sample variance of the variable x is considered. With the help of the sample mean and variance, we can compute the new value for the given value xi. After transformation, here we now find the new attribute mean to be 0 and the standard deviation to be 1. So now whatever may be the value or whatever may be the scale to which it belongs to, we can apply these two normalization techniques for reducing the range of values, and thereby we can improve our computational time. So to summarize, in this module we discussed about how real world data may exhibit multiple features or attributes. And when we are trying to do exploratory data analysis, we need to exploit the associations or correlations among these attributes, which may be done by using univariate, bivariate or multivariate analysis. And finally, we discussed about how attributes that vary with respect to their scale may be normalized to a simple range. Thank you.